Hello, BIOL1001. Welcome to Week 2, Unit 1.2. This is where we start learning about the process of science. So what actually makes good science good and bad science bad. And what we'll be learning this week is really fundamental to understanding kind of not so much what makes it good or bad, what gives us confidence in a good experiment. So what are the components of an experiment? What components do you need to have a good experiment? And that in turn allows us to assess the quality of any given scientific study. So you, as consumers of science on a daily basis, encounter different scientific claims, like the one in Chapter 1 about the effects or health benefits of caffeine. What are those based on? What's the science underlying those claims? How much confidence should you have in those claims? Those are all questions that once you understand how science works, you can begin to then answer with a certain degree of confidence. This section is also important for the course itself. As we move forward and you start doing more complicated labs, you're going to be asked to actually apply the scientific method and these experimental approaches to your own research questions. So you'll want to be able to distinguish between a question and a hypothesis and a null hypothesis, what components make a good experiment, what are the controls, what are the experimental manipulations, what are you actually controlling for in that experiment versus what are you actually manipulating, sample size. All of these things will come into play when you start to design your own experiments in the course. And so don't pay attention to this section solely for the understanding this section. You're going to be carrying these tools forward as we go through the course, okay? What's on the agenda this week? Well, you have your reading quiz. That's related to Chapter 1. You have your essential questions that you'll be doing with your group. And then you have a series of lab videos that will give you more in-depth background in terms of what goes into a good experiment and what makes science, what makes good science. And so pay close attention to those because, again, like I said, that kind of this information is going to be key for you developing your own research projects this semester. Just to kind of give you a brief overview before you get started, I was going to walk you through a little slideshow that kind of illustrates we tend to think of science as a linear process, and that's not necessarily the case. It's actually a much more complicated process, and I wanted to kind of give you a sense of how that looked. So the scientific method, as you're probably most familiar with, starts out with an observation or a question. You see something in nature, and why are there birds in this lake and not in this lake? Or why do some people get sick when they're exposed to this food but not this food? Whatever the question might be, you make an observation of nature, and that prompts you to ask a question. And then that's really what we call the exploration discovery phase. Observation is very key to doing good science. The next stage is then to come, once you have a question, to address it with a hypothesis. And you'll see when you read the chapter what we mean when we say hypothesis. But a key thing to hypothesis is that it's testable. You can actually do an experiment that will test and answer your hypothetical statement, okay? So to test a hypothesis, you design an experiment. That's what we mean when we say a hypothesis is testable. You can run an experiment to test it. So we call this the testing ideas phase. We make an observation, we ask a question, then we test an explanation for that observation. The next thing is then to draw conclusions, right? You run an experiment, it either validates your initial hypothesis or it doesn't. And from that set of data, you say, okay, well, I either support my hypothesis or I don't, and I need to think of another explanation. This is the outcomes phase. And typically, we think of this as a very linear process. You ask a question, you formulate a hypothesis, you collect data from an experiment, and you draw conclusions. That is the standard or classical sort of scientific method. That's not exactly how it works, and you'll see the process as it truly is when you start doing the science in the labs and working with your group. Because the reality is that not only are they not linear going from one way to the other, but they have crosstalk. So you test ideas that leads you to make new discoveries, new exploration, or you start exploring new aspects based on the experiments you're running. The outcomes in turn cause you to modify your experiment, to retest it. In turn, that leads to you making new discoveries. All of this stuff has a feedback loop into it that makes science much more dynamic than just a sort of linear one-way process. In addition to that, you have community feedback. You have the feedback of your peers, you have the feedback of the public, you have the feedback of advisors and review panels, all of which give you, potentially different interpretation or validation of your results. So science isn't solely an objective process. It involves a community. And so you have to consider the context in which you're doing the science. You also have to consider the feedback of your peers and the people that might benefit from the science you're doing. In whole, you have to think of it as sort of an ecosystem, right? Science isn't done in a vacuum. Some science is literally done in a vacuum, but conceptually science isn't done in a vacuum. It's done in a community. It's a communal process, and it has feedback and iterations, and it's constantly undergoing revisions and modifications to make new and exciting discoveries. That's what makes science so exciting, is that there isn't really an endpoint. It's a continuous process of discovery and learning. It's really just a method that we keep learning about the natural world by. So with that in mind, when you start designing your own experiments, don't get caught up in this bubble of having to design the perfect experiment or, everything's got to be right. It has to be good, but it also will be amenable. And you'll see that when we start doing peer reviews and all of these sort of things that give you feedback to allow you to adjust the science you're doing. So I'll stop rambling on. This video has been a little too long for the first video. Typically I'll keep them under 3 minutes, or at least under 5 minutes. But I'll shut up for now and let you guys get to week 2. Have a good week.